Welcome to e-Padasala lecture series in computer science. In this module we are going to discuss about the new paradigm called divide and conquer technique. In this module we are going to discuss about the concept of divide and conquer in algorithm study. We are going to understand the applications of divide and conquer technique using number of problems. We want to discuss the merge sort as well as the quick sort as part of this particular module. Divide and conquer is a design paradigm using which efficient algorithms can be designed. What is a divide and conquer technique? Divide and conquer technique involves three stages. The first stage is called division, where the problem is divided into a number of subproblems, and it is very important to know that the subproblem should be similar to the original problem, but only thing is it is smaller in size. Once the problem is divided, then we can solve the subproblems in a recursive manner, and once the subproblems are solved, then we can combine the solutions to get the original problem. Divide and conquer we use in our daily life many times. For example, if somebody asks us to correct 20 papers, then if we have 4 assistants, then we can divide the problem into 4. So I can give 5 papers to every assistant and I can ask them to correct, and once the correction is over I can collect everything back. This problem can be solved in many ways also. For example, if I want to find the sum of an array, and if array consists of 100 numbers, then I can divide the array into various subarrays, maybe 4 or 5. I can compute the sum of every subarray and I can get the global sum by adding the partial sum of the subarrays. This is the kind of technique we are calling as the divide and conquer paradigm. In this module we are going to discuss two important sorting techniques that are using the divide and conquer technique. So first we will take the merge sort. The merge sort involves a sequence of n elements that needs to be sorted. So we will try to apply the divide and conquer paradigm for this. So we will try to divide the n element sequence into two subsequences of n by 2 elements each. So that means we are breaking the problem into smaller problems. Then we are trying to solve the smaller problems. In other words, we are trying to sort two subsequences recursively using the merge sort, and once the subsequences are sorted, then we are trying to combine all the things to get the global sorted list. So this is what we are doing as part of the merge sort. Let us take a small numerical example to see the psychology of this divide and conquer. Let us assume that we are given an array that needs to be sorted. So you can see very well the given array consists of 8 elements. So this array needs to be divided, because division is going to be the first stage of divide and conquer. So you can see very well, now I am trying to divide this array into two sub arrays. So you can see very well the subproblems are similar to the original problem, only difference is the size of the subproblems are smaller. So again this problem can be divided. So you can see very well I am trying to divide this into two subarrays, and in the next stage again this can be divided into two subarrays, and every array has got one element, that is 18 and 26. You can observe that we cannot further divide this problem. So we stop, and then we are trying to merge this to get the sorted sequence. So that means you can see very well. So 18 is the smallest number. So 18 is going as the sorted one. Next comes 26. So you can see very well I am trying to merge these two to get the sorted sequence. Next I am trying to apply this for all other things. So that means you can see very well 32 6. So it is getting divided. So you can see very well I am trying to merge this. So now I can combine these two by merging. So you can see very well it becomes something like 6, 18, 26 and 32. This is the sorted sequence of the first half of this particular unsorted array. I can repeat this for the right hand side or right list. So you can see very well the right array 43, 15, 9, 1 is divided into two subarrays, and I can further divide this. You can see very well I can't go further, therefore I am trying to merge this to get the sorted list. So I am repeating for the other sub array. So you can see very well it becomes like this. Now I am merging everything. So when I merge everything I am getting the sorted list. This is how it goes. So now you can see exactly how this divide and conquer works. The first stage is division, where I am trying to divide the problem into sub problems. Then I am trying to find solutions for the sub problems. Then I am trying to combine the sub solutions to get the global solutions. So you can see very well this is how the algorithm for merge sort looks like. So this is the name of the algorithm. A is the array, that is the unsorted one, and P, R are nothing but the lower and upper bounds of the given array. So when P is less than R, so I am trying to divide, so preferably exactly by half. So I am trying to find P plus R by 2. I am taking the floor to avoid the fractions. Then once I have Q, my problem is now divided into sub problems, that is from the lower bound P to Q, and I have another problem, that is Q plus 1 to R. Now I have to apply this in a recursive manner. So I am just calling the merge sort from P to Q and from Q plus 1 to R. And once I recursively call this leads to the sorted array of the sub arrays. Then finally I am trying to merge everything to get the global list. So this is how the merge really works. So you can see very well what we are trying to do for merging. I am taking one element of the subarray and I am trying to take the another element of the another array I am trying to make a comparison which is a smaller one, and the smaller one goes to the top, and this process is getting repeated till the subarrays becomes exhausted. So, this is how the algorithm for the merge works. So, this is how it really works. So, you can see this is the analysis of the merge sort. So, in merge sort you can see very well the computing the middle, that is Q is equal to floor of what you say the lower bound plus upper bound by 2 takes constant time, and every subproblems I've got an instance of n by 2. Therefore, we have 2 subproblems, therefore, this becomes 2t n by 2, and merging of n elements takes n. So, that means you can see very well put together the complexity of the merge sort is something like theta of n log n. So, this is how the recursive equations looks like. Suppose if n is going to be 1, this is constant, and when n becomes greater than 1, you can see very well the recurrence equation becomes something like t of n is equal to t of n by 2 plus theta of n. We can use lots of techniques. In module 4 we discussed about the Master's theorem. So, the Master's theorem can be applied for these recurrence equations. This is A is equal to 2. So, this is B is equal to 2. So, when we apply the Master's theorem, so you can observe that the result is something like theta of n log n. Probably you can recollect, we also discussed about the complexity analysis of merge sort using the recursive tree method. So, you can see very well this is a problem of size n. So, in the next stage it becomes n by 2 n by 2. So, that means it becomes n. So, here it becomes n by 4 n by 4 n by 4 n by 4. It is going to be 4 into n by 4, that is going to be n. So, that means you can see very well at every stage the cost of recursive tree is n. You have what you say log n as a depth. So, therefore, the cost becomes something like n into log n. In other words, the complexity analysis of merge sort is theta of n log n. It is applicable for both what you say best case, average case as well as the worst case scenarios. The next important sort is quick sort. Quick sort is supposed to be the fastest sorting algorithms in practice in average case, but in worst case the algorithm complexity is just like any other sorting techniques that we discussed, that is order of n square, but this scenario arises very rarely. What is the idea behind quicksort? Quicksort was designed by Hoare, and the idea is very simple, where we have to pick up a element called the pivot element, and the idea is very simple, divide and conquer. We have to divide the problem into subproblems. So, here the list is divided into 2 disjoint groups, such that the first list will have elements except the pivotal element whose are lesser than or equal to the pivot, and the another list is supposed to have all elements except the pivot that are greater than your pivotal element. So, in the division step, what we are trying to do is, unlike In merge sort, where the division is carried out in an even manner, in quick sort, division is carried out using the pivotal element like this. Once we have the division, then we can conquer by repeatedly sorting S1 and S2 using the same concept, and once this is over, we can combine everything. That means sorted list S1 followed by the pivotal followed by the sorted list S2 to get the final sorted array. So, this is the core theme of this particular sort. So, we have to find pivotal element P, and on the left hand side all the elements should be lesser than your pivotal element, and on the right hand side all the elements should be greater than your pivotal element. This is the idea. How to partition? This is the most important question, and once we have an method for partitioning, then the quicksort algorithm becomes very easy. So, all we have to do is we have to partition, and once we partition we have subarrays. So, we have to call quicksort in a recursive manner, so that the sorted list becomes sorted and finally the assembly can be carried out. So, in this algorithm the more crucial thing is partition, how to partition the array using the pivotal concept. A Lomoto partitioning algorithm is one of the popular partition algorithm, where the partition is carried out like this. So, just recollect that partitioning means we have to find a pivotal element, and all the elements on the left hand side should be lesser than that, and all the elements on the right hand side should be greater than your pivotal element. In Lomoto, the partitioning is carried out like this. I am just making an assumption that the first element is going to be the pivot element P. Then a pointer is assigned to the next element, and I am checking A of I is not less than P. That means A of I is going to be 93, which is not lesser than pivotal element P. Therefore, I am incrementing I. So, you can see very well I is incremented to the next position, and now A of I is 57. So, that means you can see very well A of I is lesser than P. Therefore, what I am trying to do is I am incrementing the pointer S, so that it points to the next element 93. The most crucial aspect in quicksort is partitioning. We will discuss one way of partitioning called the Lomoto algorithms. In Lomoto algorithm, what we are trying to do is we are taking an array like this, and the first element 60 is assumed as the pivotal element. Then I am setting two pointers S as well as I, and the process involves checking the A of I is lesser than the pivotal element or not. In this case, A of I is not lesser than pivotal element. Therefore, I am incrementing I. So, now you can see very well the I is incremented to 57, and you can observe that A of I is lesser than pivot element. So, that means you can see very well the pointer S is incremented to the next element. So, you can see very well. So, now I am swapping this. So, the list becomes something like this. So, again the process is getting repeated. So, A of I is not lesser than your pivotal element. So, you just increment I. So that means your pointer now points to 90, and incidentally a of I is not lesser than p. Therefore, I am incrementing I again. You can see very well it becomes something like this. So now a of I is going to be lesser than p. Therefore, I am incrementing s. So my process becomes something like swap. So I am getting this list. Now I am swapping what you say the pivotal element with a of s to get the final list like this. So now you can see very well this is the list where you have the pivot as 60 and all these elements are going to be lesser than 60 and all other elements here on the right hand side are greater than 60. In other words, this element 60 is in its correct positions. So that means this becomes a sorted list and these things are yet to be sorted. So this process can be repeated till what you say the entire thing is sorted. So this is how the algorithm is looking like for Lomoto. So you can see very well the input array is A with lower bound L as well as upper bound R. So that means now you can see very well first element, that is A of L, is assumed to be the pivotal element and S points to the first element of the list, and you can see very well I is a pointer that starts from L plus 1 to R, and as you have seen in the numerical problem, we are checking whether A of I is going to be lesser than P. If that is the case, I am just incrementing S and I am swapping A of S with A of I, and if not, this process goes on. So you can see very well once you have the final exit of this loop, then A of L is swapped with A of S and S is being returned as the pivotal element. This kind of algorithm is what we are calling as Lomoto algorithm. We can also partition using another algorithm. The original algorithm by Hoare himself is called the Hoare partition algorithms. This is called two directional algorithms. This is also another way of partitioning. Let us quickly go through what exactly this is. Again, this algorithm takes an unsorted array as the input. So we can select a pivot in an arbitrary manner, but let us take the first element itself as the pivot element as suggested by the original author. So we will take the first element as the pivotal element. The logic is very simple. Left hand side should be lesser than the pivot. So that means we have two groups, left as well as right, such that the left group will have elements lesser than the pivot element and the right group will have the elements that are greater than the pivot element. So I am taking 26, the first element of the unsorted array, as a pivot. I am putting the pointers left as well as right, such that left will scan the array from left to right and the right pointer will move from right to left looking for the candidates for exchange. How the exchange is taking place? It is something like this. If the left element, that is the element that is pointed by the left pointer, actually belongs to the left group, that means the elements are going to be lesser than the pivot element, then the left pointer is incremented, that is left becomes left plus 1. If the right element that is the element that is pointed by the right pointer belongs to the right group, then we will decrement the right pointer, that is the right becomes right minus 1, and exchange will take place whenever we encounter elements that belong to the other group. Suppose if this scenario is there, then we are going to exchange. So, now we will apply the procedure for this. Now, the left pointer points to the 33. 33 is actually greater than 26. Therefore, it belongs to the right group. Here, the right element that is pointed by the right pointer 23 is actually lesser than 26. Therefore, it should go to the left group. So, that means we encounter situations where every element belongs to the other group. Therefore, we are carrying out the exchange. So, now you can see very well this 23 comes here and this 33 goes to this particular side. So, now you can see very well after the exchange we are just incrementing the left marker as well as we are going to decrement the right marker. So, now you can see that the left element is 35 and the right element is 12. Again you can see very well the left element 35 is actually greater than your pivot. That means it should go to the right group, and this number is lesser than 26. Therefore, it should go to the left group. So, unfortunately, this order is not maintained. Therefore, we are again swapping. So, again we are exchanging and we are getting a scenario like this. And when we keep on doing like this, we encounter a scenario where the left and right cross. That means now we do not have any provisions to go further. So, whenever we have such a situations, then we are simply swapping the right with the pivot element. So, that means now you can see very well, now these two crosses each other. Therefore, I am just swapping this 19 with the pivot element. So, that means the resultant becomes something like this. So, now you can observe that the pivot element is going to be 26. So, that means you can see very well on the left hand group all the elements are going to be lesser than 26, and on the right hand side all these elements are going to be greater than 26. That means that the 26 is in its correct positions. So, that means now you can see very well this is the correct position of this element. So, now you can see very well this unsorted array is now divided into a scenario where this S1, that is the left group, and your pivot element and your right group, that is S2, is present here. So, now you can recursively apply this quick sort to these arrays without what you say affecting this pivot, and repeating this kind of procedure we can ensure that the sorting is carried out. Again you can see very well this is how things are being done. So, again if you apply this procedure to this, it comes to be seen that 19 is going to be the pivotal element of this, and 33 is going to be the pivotal element of this, and now you can see very well these sub arrays are sorted. Therefore, when we combine everything we get some sort of a sorted list. So, this kind of procedure is what we are calling as the quick sort. So, just I am just recollecting that. So, you can see very well first step is going to be the partitioning. So, we have seen that partitioning can be carried out either by the Lomoto algorithm or by means of the Hoare algorithm, and once we have the partitioning, and it becomes very simple that the sub arrays needs to be recursively called, and finally once these things complete, finally you can see that the whole thing is sorted. Fine, this is the complexity analysis of the quicksort. So, as I said earlier, the efficiency of quicksort depends wholly on the partitioning element P. So, this is the worst case scenario. So, in worst case scenario, the complexity is something like order of n square. Why? For example, let us say if the pivotal element is happens to be the first element. So, that means your left hand side list S1 consists of 0 elements and all the elements goes to the right hand side. If that is the case, then the partitioning is going to be worse. So, in that case you can see very well your equation becomes something like T of n is equal to T of n minus 1. So, that means almost all the elements are on one side and on the right hand side you have that unbalanced scenario. If this is the case, you can see very well this is how your recursive equations looks like. So, T of n minus 1 is going to be T of n minus 2 plus cost of n minus 1, and if you repeat this you can see very well this turns out to be the order of n square, which is going to be the worst case. The best case arrives when the tree is actually a balanced one. So, that means you can see very well you have a typical scenario of T of n is equal to T of n minus 2 by plus C of n. So, in that case you can see very well it is going to be the order of log n. The worst case never happens, therefore, we can come to a conclusion that quicksort is always better compared to the other things. So, you can say that the quicksort is going to be the optimal in the sense that the complexity is going to be the order of n log n. In summary, we can conclude that divide and conquer is a better paradigm, and we can develop lots of better algorithms. So, in this model we discuss about the merge sort and quicksort, and the complexity analysis is very important. So, Master's theorem can be effectively used for this. So, with this we conclude this module. In the next module we will discuss some more aspects of divide and conquer strategy. Thank you very much.